Hello, friends. This is Jim with Science Talk. I want to share this article. Now, it comes from 2017, but oftentimes you hear people saying, well, it's just natural cycles. Humans aren't doing anything, and it's just all BS, and you guys want your funding, and so on and so forth. Well, Union Concerned Scientists put together this report. How do we know that humans are the major cause of global warming? Now, you may recall when I did my segments on regression that oftentimes what we do, not often, what we try to do every time is for every parameter that we have in a model, we try to assess the contribution that parameter gives in the observed responses. So when we say humans are the major cause of global warming, we're basically meaning more than 50%, basically. Not the, humans don't explain 12% of the variation. It's something, but it's not major. When we say major, we're talking a good chunk. So, how do we know humans are a major cause of global warming? In a brief look at the content. Unprecedented warming. Earth's surface has undergone unprecedented warming over the last century, and especially in this century. Every single year since 1977 has been warmer than the 20th century average, with 16 of the 17 warmest years on record occurring since 2001. You can probably make that 17 of 18 when you include this year. 2016 being the warmest year on recorded history. A study from 2016 found that without the emissions from burning coal and oil, there's very little likelihood that 13 out of the 15 warmest years on record would all have happened. As any farmer can tell you, the natural patterns of climate have been altered. So, I'll bring your attention to this little diagram here. And what we're seeing here, got marine, land, river, mountain, okay, that kind of stuff. We see a decrease in sea ice area. We see an increase in water vapor. Water vapor is a greenhouse gas. Okay? As you warm up the air temperature, warmer air can hold more water vapor. More water vapor means more precipitation. We see a decrease in glacier volume. The temperature over land is increasing. Snow cover is decreasing. Right? That kind of makes sense. If the glacier volume is decreasing, snow will decrease. Sea levels going up. Ocean heat content is also increasing. Remember, I have discussed with you in prior segments that the specific heat of water is much higher than air. So it takes a considerable amount more energy to increase a given volume of water 1 degree C than that same volume of air. This is a lot of heat packed in here. Sea surface temperature, SST, is increasing, as is the marine air temperature is increasing. So I think if we clicked on one of these things here, yeah, see there, it's just made a little larger so we can see air temperature in the lowest few kilometers, basically the troposphere. That's where air temperature has increased. That's what the measurements are. So let's see, how do we get back out of this thing? Okay, it just opened up a new tab, duh. Okay, I'll just leave that up there. So is any so we know that warming and cooling has happened in the past, right? We know the Earth has gone through cycle, but again, it's that rate of change I keep stressing. Many factors called climate drivers can influence Earth's climate, such as changes in the sun's intensity, volcanic eruption, changes in the Earth's orbit. I don't think that's mentioned in this report. But the Milankovitch cycles, well as heat-trapping gases in the atmosphere. What's causing today's unprecedented warming? A human's part of the cause. Scientists have devised different methods to answer this question. Meteorologists and oceanographers compare the climate pattern they observe with patterns developed using sophisticated models of Earth's atmosphere and ocean. By matching the observed and modeled patterns, scientists can positively identify the human fingerprints associated with the changes. They can also attribute the proportion of those changes to human activity. That's that contribution of each parameter to the overall observed response. So, this is a look at the IPCC reports over time. The amount of human-caused warming is indicated by how much blue is in here. 1990, the report did not quantify, bring it up a little larger. Yeah, the report did not quantify the human contribution to global warming. In 1995, the balance of evidence suggests a discernible human influence on climate. And then look what happens as we get 2001, 2007, 2013. Human-emitted greenhouse gases are likely 67 to 90% chance responsible for more than half of Earth's temperature increase. More than half. There's that 50% threshold I mentioned. Human-emitted greenhouse gases are very likely, so going from likely to very likely, at least 90% chance responsible for more than half of Earth's temperature increase since 51. 2013, human-emitted greenhouse gases are extremely likely. At least now it's up to 95% chance. And the IPCC downplays things. So this is what the IPCC is reporting. Now this is 2013. It's been 5 years since. We might even see this number up to say 98%. So that's what that the changes to the IPCC report. Okay. The fingerprints that humans have left on Earth's climate are turning up in a diverse range of records. It can be seen in the ocean, the atmosphere, and Earth's surface. Scientists agree that today's warming is primarily caused by humans putting too much carbon in the atmosphere, burning the fossil fuels, cutting down trees, forests. You know what's going on. Scientists have gathered evidence and have improved their methods for teasing apart natural and human factors. In other words, being able to tell how much is due to natural variations and how much is due to human activity, i.e. the warming that we see. Today's scientists have very high confidence about human-caused global average surface temperature increase, a key climate indicator. They have reported on their growing confidence through successive climate assessment of the Intergovernmental Panel of Climate Change, IPCC. And I just showed you that diagram there. Direct evidence of human contribution to atmospheric CO2. Now, you've seen this graphic before. I've shown this to you in a previous video segment. Here's 400 parts per million CO2 level concentration, this dashed line. Okay, the upper layer is 2016, and then late 2016, and then this is also, these two are 2016, and we have 2014, 2013, 2012, 2011. In other words, for 2016, we definitely see above 400, basically up to 404 parts per million, and we had some measurements, below 400. So this is showing the thickness of the color band, is showing the range of values, and this 400 is the threshold that we crossed over. So carbon dioxide moves permanently above 400 parts per million. That's what this is basically saying. So that's what that threshold is. And the organization 350.org, well, as you can see, it doesn't even go down to 350. 350.org was basically saying that's what we needed to keep CO2 levels below it to avoid catastrophic climate change. Well, we just blew past that, and we're blowing past 400, and we're now steadily above 400. Recent data has this up to 411, anywhere 411, 421. We're blowing past this. CO2 is the main heat-trapping gas, largely responsible for most of the average warming. over the past several decades, but you have to also include methane, CH4. The atmospheric concentration of CO2 has increased dramatically from a pre-industrial era, 1,000 to 1750, of about 280 to today's 400. Scientists warned for years about this threshold, this dangerous threshold. But with the accelerated pace of emissions, the question changed from whether we would reach CO2 concentrations above 400 ppm, parts per million, or to when. The Arctic reached 400 parts per million in 2012. That's before. In 2013, the Mauna Loa Observatory in Hawaii recorded more than 400 ppm. In March 2015, global averages reached this threshold. Averages. So this is looking at averages here. And in September 2016, the world reached a point of no return. CO2 concentration levels are unlikely to dip below 400 parts per million again. We know human activities are driving the increase in CO2 concentration because atmospheric CO2 contains information about its source. Now, as you know, where you collect the CO2, you can actually say where it came from. Scientists can tease apart how much CO2 comes from natural sources and how much comes from combusted fossil fuel sources. Carbon from fossil fuels has a distinctly different signature. Essentially, the relative amount of heavier or lighter atoms of carbon. Technically, and let me scroll down here and we'll click on this over here in a moment. This little kind of looks like a Hershey kiss here, this little symbol. That's read as Del. It's basically a Greek letter, but it's called the Del 13 carbon. This goes back to isotopic fractionation. You've heard me mention with you before, and I did a video segment on isotopic fractionation, and I probably will revisit that. The more negative the Del 13C, the higher the proportion of carbon from fossil fuels. I'm not going to get into, the negative. Basically, we're looking at the ratio. The Del 13 fractionation ratio compared to the common isotope of carbon, which is C12. Notice it's carbon 13, not carbon 14. Carbon 13 is actually it occurs less frequently as an isotope than C14. But because of the C14 being more abundant, we can use that for dating purposes. Right? You can use C14 to carbon date something. Over the years, the Del 13 carbon has decreased while the overall amount of CO2 has increased. This information tells scientists that fossil fuel emissions are the largest contributor of CO2 concentration since the pre-industrial era. Okay. So, let's see if we can click on this. And let's see if we can tell what's going on here. Okay, so this is the CO2 in parts per million. And as we can see, we see this increasing here. I'm not sure, to be honest, I'm not sure what this is. Oh, that's the Del O2. Okay. That's delta oxygen. Okay, so this is oxygen levels. So basically, okay, so this is CO2. Excuse me, this is CO2 in green increasing, and the parts per million of the delta oxygen is dropping. Okay, I'm not sure what that is, what the significance of that is, to be honest, but here is the Del 13, and this is per million that they're talking about. It's going from minus 7.4 down to minus 8.4. So this decrease is showing that the source is fossil fuels. That's the take-home message from this graph. CO2 levels overall increasing. And this tells us we know it's from fossil fuel because of the decrease in the fractionation. So going back, natural and human factors that influence the climate, known as climate drivers. Emissions from cars and power plants and an increasing amount of radiation the sun emits are examples of forcings that drive temperature rise. The first one by trapping heat, the second by increasing energy, which is translated into heat. Volcanic events and some types of human-made pollution, both of which inject sunlight reflecting aerosols, i.e. tiny particles into the atmosphere, will lower temperatures. An example of forcings that drive decreases in temperature. And this is part of the silly notion of geoengineering. Let's just put a pile of aerosols into the atmosphere. Let's see, the sulfur dioxide variety and other species of chemicals. And that will reflect sunlight and cool the planet down. Well, what they don't take into account is what happens when that stuff washes out of the atmosphere. It gets into the soil, and it then messes with the physiology of the plants. That can cause crop failures, and when you go up the food chain, that causes problems. A recent study found that almost 2/3 of the impacts related to atmospheric and ocean temperature can be confidently attributed to anthropogenic forcing, i.e., humans. Okay. I don't need to enlarge this one. This is the observed warming. Okay. This is from greenhouse gases, other anthropogenic forcings, combined anthropogenic forcings, natural forcings, natural internal variability. In other words, think of this as a range. Right? So this is a range. With this being kind of like the average, so go from here to here, what have you. But it's also superimposing the natural forcings on it. And as you can see, this is the observed warming. This is the greenhouse gases is more than what we're observing. Basically, what this is telling us is that greenhouse gases and humans are driving things. That's what this is telling us here. If we had greenhouse gases like a small bit like out to here, then it's not driving it. But as we can see, it's significant, as is combined anthropogenic forcings. Natural climate drivers include the energy from the sun, aerosols from periodic volcanic explosions, dust, salt spray, natural carbon cycle processes like termite mounds in Africa that emit methane, or tiny organisms in the ocean surface that take up CO2 and variation in snow and ice cover that change how much the Earth's surface reflects the sun's energy back into space. And that is called albedo. So, for example, the ice sheets in Greenland and Antarctica reflect a lot of sunlight energy back into space. So that's called albedo. And reflecting that sunlight energy, usually in the form of long wave radiation, helps reduce the energy, helps keep things cooler. Incoming solar radiation is called shortwave radiation, and then it's emitted back, reflected back in the long range. Okay, so we have here, let's see if I can get that to enlarge. That's not going to enlarge. Well, that's the one I want to enlarge, wouldn't you know it? Effective radiative forcing, this is in watts per square meter. That's what the units are here. And we're going from 1750 to basically 2007, or okay, 2011. That's the year is here. So we have a bunch of various factors here. The purple is total anthropogenic forcing. We break it down to land use. Can't really read that, to be honest. Volcanic, and so on. So there's a bunch of I wanted this is the one I wanted to enlarge, and I won't enlarge, wouldn't you know it? Heat trapping emissions far outweigh the effects of other drivers acting on Earth's climate. Volcanic eruptions account for the cooling spikes. These guys. Seen in the graph in 1883 and 1991. Well, 1883, Krakatoa. There it is. Okay. Krakatoa, the island exploded, basically. So Krakatau in Indonesia and Mount Pinatubo in the Philippines can be seen as two large downward spikes in volcanic data. These particles prevented the full energy of the sun from reaching the surface and created a cooling trend for several years. So Pinatubo, Krakatoa, okay, they far eclipse what Mount St. Helens did. Okay, we're pretty much aware of the, burning fossil fuels, burning forests, cutting down forests, etc. Fossil fuel burning by humans emit tiny particles in addition to releasing CO2. Some particles reflect the sunlight back to space as aerosols, similar to what the volcanic particles, having a cooling effect, but the CO2 far outweighs any effect from the aerosols. Black carbon, called soot, commonly known as, absorbs sunlight, drive temperature rise, leading to local warming of the atmosphere levels where the soot particles circulate. Both types of human-created particles lead to a decrease. Very likely it would have been even more warm in the past 60 years if it were not for aerosols. Now, think about that. Some of these drivers result in warming, others in cooling. But the net sum is warming. Right? Think of, if I have something that's plus 5 and I take away 3 from it, I have still a net gain of plus 2, right? So there is a net gain in warmth. Even when you subtract out the aerosol, it's still warming. So the accumulation of human-released heat-trapping gases in the atmosphere is so large that it has eclipse-swamped other climate drivers, leading to observed global warming, including the aerosols, right? It's outpaced those. Okay, so now I want to, mathematical models allow scientists to simulate the behavior of complex systems and explain how these systems respond to natural factors. Let's take a look at this graphic here. So we're looking at global averages, basically. So they have ocean, land, ocean and land, and then ocean heat content. So the observations is the black lines in here. The blue spacing, this is again a range in the data, is using models using only natural forcings, and then I guess it's pink, models using both natural and anthropogenic forcings. These gray, darker gray, and black are just basically the data sources that were used. So we have here on the vertical scale temperatures, and it all go from 1850 to 2011, for all of them, except for this one, which goes to 1950 to 2011, because this is where we have reliable data for it. It's probably more like 1948 or so. And OHC is probably overall heat content, ocean heat content, and this is in 10 to the 20-something joules. Joules would be in energy. That looks like a 10 to the 22nd joules. So what do we see from here? If we just look at natural forcing, temperatures stay fairly constant. In these three panels, temperatures staying fairly constant. We can, yes, we see some up and down peaks and lows. That's to be expected. You have seasonal effects, summer, winter, and all that kind of stuff. Warms up in summer, cools down in winter. That's to be expected. You throw in other natural forcings would be El Nino, Southern Oscillation, and so Pacific Decadal Oscillations, North Atlantic Oscillation, things like that. So it's fairly, so if we were to, fit a regression line through here and test the significance of the slope, we'll probably find that the slope is equal to 0, which means it's basically constant. But once you put in you combine the anthropogenic forcing, look what happens. Temperatures goes up. And we start seeing this really rapid rise from about 1930 or so. It really starts to kick it into gear. And if you look here, the ocean, again, goes starting about 1930 here, where we start. It looks like an all-in, about from 1960 on is where we see a sharper increase in the slope. Now, the ocean heat content. This is the telling bit. Right? Go back to what I always stress: the specific heat of water, the heat capacity. Water holds a lot of energy. In fact, now recent studies have indicating that the water, that the ocean is holding a lot more energy than we previously thought. So, our bacons are basically being saved by the fact that the ocean are absorbing a lot of the heat. It's not staying in the atmosphere. We'd be in deep, deep trouble if a lot of that energy was not absorbed by the ocean and stayed in the atmosphere. It would be uninhabitable for humans. So this is a very important graphic here. For a computer model to accurately project the future, climate scientists must first ensure that it accurately reproduces already observed temperature changes, i.e., they need to see if it has to see they work well. The scientists working in the IPCC assessments have carefully documented observed changes in air temperature, ocean temperature, ice retreat, sea level rise since the past century. Then they use computer models to compare everything, the observed changes with natural climate drivers, human climate drivers. The IPCC concludes the effects of greenhouse gases together with those of other anthropogenic drivers have been detected throughout the climate system, are extremely likely have been the dominant cause of the observed warming since mid-20th century. Scientists reached this conclusion after contrasting observed changes to different types of drivers. When climate models include only recorded natural climate drivers, the models cannot accurately reproduce the observed warming of the past half century. When the models also include human-induced climate drivers, then they accurately capture recent temperature increases in the atmosphere and in the oceans. And when all the natural and human-induced climate drivers are compared with one another, the dramatic accumulation of carbon from human sources is by far the largest climate change driver over the past half century. In other words, to sum up all that, what was just stated, scientists are able to tease out what's natural, what's human, and then when they factor it all in and analyze it all, they say humans are the main drivers of what's going on, of the drastic increase in temperature, and especially the CO2 levels. Over the years, the models of attribution science, that's basically, how much variation in the of the observed responses can be explained by this parameter. How much does this parameter explain the variation in the observed response? So it's basically, like I said in my regression video, how much does each parameter contribute to the observed response? That's basically what attribution science deals with. So those models have become sophisticated, as to be expected. In addition to attributing global warming to human-caused emissions, they're also able to determine the contributions of global warming to extreme events, floods, heat waves, storms. Again, this one will not enlarge. The confidence and capabilities for attribution of specific events to anthropogenic climate change. Goes from low to high, low to high. So this would be basically the median. And like extratropical cyclones, extremes, looks like snow and ice, wildfires, tropical cyclones, extreme rainfall, droughts, extreme heat, extreme cold, and I really can't read what's in the black circle there. So basically what they're saying is extreme heat, extreme cold are bigger contributors to You could say the kind of the one-offs or the rare events that take place. So as you move this way, it's higher and higher. As you move this way, it's higher and higher. So understanding the effect of climate change on any event type. So as you move up here, the extreme temperature, hot and cold, drive it the most. Wildfire, surprisingly, does not. Now, probably because of the soot that wildfires can create and place into the atmosphere. But taken as a percentage, it's probably not as bad. Extra tropical cyclones, cyclones are heat distribution mechanisms. Extreme snow and ice, that's basically the once in a century blizzard kind of stuff. Extreme rainfall, again, sort of like an extra monsoon, if you will. Droughts, though, you notice how drought is edging out the precipitation, right? Extreme snow and ice, extreme rainfall, this is like precipitation events. The droughts is a big driver, and we're seeing more and more drought. Climate models are basically saying that we're going to see more wildfires, we're going to see more droughts, we're going to see more extreme ranges in temperature and etc. In 2016, the National Academies of Sciences, Engineering, and Medicine released a report analyzing the state of extreme event attribution science. The report showed that scientists can evaluate the effect of climate change on a single extreme event, how human-caused emissions can increase the likelihood of that event to happen. So another way of looking at this graph is that what is the likelihood of these things happening due to what humans are doing? That's another way of looking at it. So in addition to being a driver, how much of this driving can be caused by humans to create the driver in the first place for an event? So it's obviously still in infancy, so it needs to be refined, but you get an idea of the different factors and how they can affect overall what's going on. So what the takeaway is, okay, we have an extreme event, and this can impact climate change, but then on the flip side of it, the likelihood of these extreme events taking place, what is the likelihood that they take place in the first place due to human activity? I hope that clarifies what the essence of this graphic is showing. So what are some of the solutions? Okay, we are the cause, we are also the solution. Knowing the human activity is the main driver of global warming helps us understand how and why climate is changing, and clearly defines the problem as one that's within our power to address. We cannot avoid some level of warming caused by the heat-trapping emissions already present in the atmosphere, thermal inertia, some of which, such as CO2 and nitrous oxide, last for hundreds of years or more. More aggressive measures to reduce emissions and adapt to those changes we cannot avoid, but we have a small window to avoid truly dangerous warming and provide future generations with a sustainable world. And it goes on to talk about the Paris Agreement of 2015, to keep reducing emissions, to reduce the emissions, to keep it under 2C, optimally under 1.5 C, but we're already at 1.3 C, so we're probably going to blow past 1.5. So now we got to keep it under 2, and I don't think it's going to happen, to be quite blunt. They're throwing an optimistic note here. I'm not sure it's warranted. We can reach that goal through immediate and sustained action to reduce our heat-trapping emission, adopting technologies, increase energy efficiency, expanding our use of renewable energy, and slowing deforestation, etc. Yeah, but in order for this to happen, we need politicians to become brave and to grow a pair and implement policies to actually have this happen. And yes, I did a story about China, but I'm not really seeing a whole lot, especially not here in the U.S. Germany has decided to shutter all its nuclear plants, but nuclear energy, aside from the radiation concern, nuclear energy really does not release greenhouse gases. But Germany is being aggressive with the solar panels and renewables, which is good, but they still have the power plants. It's not going to happen overnight, but it really needs to step up the pace of replacement. It really does. And as you can see, this report was last revised on August 1st of 2017. So you can see the URL up here. Okay. But if anyone starts arguing with you that, oh, we don't know the humans doing it, blah blah blah, you can cite this and basically say, well, we've got the evidence, and we got the data to back it up. Scientists don't just make stuff up. Okay? Scientists do not do what politicians do. Politicians have a conclusion, and then they create the data to back up the conclusion. Well, that's not science. Science, we collect the data, we analyze it, and say, oh, what does this tell us? And in the case of climate, it's telling us we're warming the freaking planet up. That's what it's telling us. So I hope you found this informative, and we'll talk soon. Thank you for your time. Hello folks, this is Jim asking for your help. I want to grow this channel significantly. I want to increase the number of people who subscribe to my channel. I want to increase the number of people who are supporting patrons on Patreon for this channel. Patreon.com/Science Talk with Jim Massa. I do not receive funding of any sort from anyone. So the information I share with you is the information as found published in the peer-reviewed journals. No propaganda, no BS, just the science, and of course I give you my interpretations and analyses based on my experience as a scientist. So please tell others of the work I do here, tell others of my channel. Share my videos, post them on other social media platforms. But we need to disseminate this information to more and more people, to a wider audience. And I need your help in doing that. For those of you who are already patrons and support me on Patreon, thank you. Thank you for your support and continued support. Together we can do this. So you'll find details in the description box below, how to support me on Patreon. And thank you. Thank you for your help. Thank you for your continued support. It does mean a lot to me. We can do this.